So our goal for the day is to cover two topics, a product theorem, which is going to help us calculate derivatives, and also to talk a little bit about higher order derivatives. These are also our keywords for today, so today only two big ideas. So here's a little motivation first. Suppose we need to find the derivative of x times sine of x. Well, I know what the derivative of x is. That first one's easy, it's just 1. And I also know what the derivative of sine of x is. That one's easy, that's just cosine of x. So maybe it's as easy to take the derivative of a product, we just take the product of the derivatives. Maybe this is going to be true. This is just going to be 1 times cosine of x, and we can all go home. Nope. Not so easy, not so lucky. It's not going to work out like this. It's a little more complicated, but not too bad. So the product theorem for derivatives says that the product of two differentiable functions f and g is differentiable, and we can figure them out using this formula. If we have f times g, its derivative will be g times f prime plus f times g prime. So it's kind of this mixture of the derivatives and the original function. We will talk a lot more in class about why this sort of makes sense, but for now, just think about how to put the things together. So the way you want to remember this is the derivative of f times g is equal to the first function times the derivative of the second, plus the second function times the derivative of the first. So let's try this theorem out. So suppose we have a function h of x which is equal to x times sine of x. The first thing is to recognize that this is indeed going to be a product of two functions. We have the function x times the function sine of x. So here in our example, what we have is we have f of x is equal to x, and g of x, our other function, equals sine of x. And the first thing we want to do is we want to compute the derivatives. So the derivative of the first function, nice and easy, is just going to be 1. And the derivative of g of x isn't so bad. It's just going to be cosine of x. So now to compute the derivative, what we need to find is we take the derivative of the product of these two functions is going to equal, according to our theorem, the second function, g of x, times the derivative of the first function, plus, now we keep our first function without taking the derivative, and we multiply that by the derivative of our second function. So when all is said and done, we end up with just sine of x plus x times cosine of x. And this will be a pattern we're going to repeat quite often. Now there is a product theorem for integrals that says if you want to take the integral of this mess of things right here, and you can recognize that, then that integral, the antiderivative, will be f of x g of x plus c. This is just because integrals and derivatives are almost inverses. It's really hard to see, it doesn't occur very often, we're probably never going to use it, but in Calc 2 you really start to make use of this idea. In order to use it now, what you'd have to do is you'd have to want to take the integral of sine of x times 1 plus x times cosine of x dx. You know, so that you could see that here we have a function and its derivative. Here we have a function and its derivative. So of course this has to just be x times sine of x plus a constant. Really hard to recognize this out when you're integrating functions, so the integral formula is not going to be useful. But the derivative one is. So let's go back and practice that some more. So let's practice taking the derivative of a product again. So the first thing is to recognize that we have two different functions here. And what we're going to do is we're going to do this one a little bit quicker this time. I'm not going to write out all my f's and g's in between. We're just going to do it a little faster. But I encourage you to take your time and practice if you need to. So here the derivative now of this function j of x, well, will equal, so what we need to do is we need to match up our g of x function to start, so 3x to the 4 minus x. We multiply this by the derivative of our first function, will be 5x to the 4th, and we're going to add to this our first function, x to the 5th, times the derivative 12x cubed minus 1. That's a very bad cubed. And so usually this is how we do it. We write it all out fairly quickly without doing all the f's and g's in between. So let's do one more example here. So here we actually have a product of 3 different things. There's 3 different products going on here. So what we want to do though is we want to think of it as a product of just 2 functions. So our first function will be x times sine of x times our second function, which will be the x squared minus 3. So that when we take the derivative here of our function, what we need to do is first we just list our first function, x squared minus 3, and we need to multiply this now by the derivative of our second function, x times sine of x, and we'll go ahead and add to this our first function, x times sine of x, times the derivative of our last function, which in this case will be 2x minus 0. And so the key thing here is that in order to keep computing, what we need to do is we need to figure out the derivative of x times sine of x. And if you remember, we computed this earlier using the product rule. So what we said was the derivative of this function is going to be sine of x times 1 plus x times cosine of x. And so now what we can do is we can insert this above. So this means that the derivative of our original function was going to be x squared minus 3 times sine of x plus x times cosine of x plus x sine of x times 2x. We made it. But this can happen now. Now we can start taking derivatives of more complicated things, so we might have rules within rules. So product rules within product rules and other such things, and it's going to be a good time. So this is one of your homework problems rather than problems from the book for tomorrow for you to try. So the question is, if f of x equals sine of x times cosine of x, so we have a product of functions, then what can you say about its derivative? Which one of the following do you think is going to be true? So you should try computing the derivative and deciding which of these you think are true, and we'll discuss it tomorrow in class. So now for something slightly different, what we want to talk about are derivatives of derivatives. So for example, we started with a position function, we took the derivative and we found that this was velocity. We can also take velocity and find that its derivative is going to be acceleration. So let's look at this in a nice table form. So what we have here is a position function. We can start by thinking about it as a zeroth derivative, so there's no derivative symbols floating around. And we can see it in different ways. So sometimes we just write y, sometimes we write s of t, y of x, or f of x. When we take a derivative, we have several different notations. So here we have the prime style notation, so we have y prime. And here we have what's called Leibniz notation, which uses d's for derivatives. But as I said, if we take the derivative of velocity, we're going to get acceleration. And acceleration can be thought of in 2 different ways. Acceleration is going to equal the first derivative of velocity, but acceleration, it's the first derivative of velocity, so it's the second derivative of our position function. If you take the derivative of position, you get velocity. The derivative of velocity gets acceleration. So that's why we write a second prime symbol down here to say it's a derivative of a derivative. Leibniz notation here, the 2, means it's a derivative of a derivative. Same over here. Well, we've done it twice already. Let's take the derivative again. So we can take a third derivative. Physicists will call this either jerk, jolt, surge, or lurch, depending on your physics preference there. And we have 3 primes to indicate it's a third derivative. Usually what we do is we start putting this in a parenthesis, right? We don't want to put a number up there by itself because that indicates, repeat the function a few times. So this 3 in parentheses indicates derivatives. Leibniz sticks with numbers, puts them up there to indicate how many derivatives we've done. Well, we've taken a third derivative. Let's take a fourth. So we're motoring along with a fourth derivative. It's called either jounce or snap. By now, almost everyone uses numbers up here. You don't want to write 4 primes up there. That would just be ridiculous. Well, what do you think the derivative of snap is? Of course you're correct. The derivative of snap is crackle. And of course we know what happens after snap crackle comes. Certainly you've guessed it. After snap and crackle comes pop. After you pop, you lock, and of course after you pop and you lock, then you drop. Okay, so after you pop, lock, drop, the next two aren't that impressive whatsoever. After drop comes shot, and after shot comes put, and after that we stop naming them, okay? I don't know what the takeaway from this is. I guess one of the takeaways is that we can write any derivative we want with an n in this notation for n primes, or taking n derivatives. And of course we can also take away that physicists are so funny. Physicists named these, not mathematicians, so we'll let them get away with it. You may want to remember drop, though. Don't forget drop. So let's go ahead and try to compute some derivatives. So first of all, we have our function f of x equals x cubed plus 4x squared plus 2. So I'm just going to rewrite our function here so we can sort of see what happens as we take derivatives. So when we take the first derivative, we just proceed as usual. The derivative of x cubed is going to be 3x squared, plus now we get 4 times 2x plus 0. And cleaning this up a little bit, 3x squared plus 8x is all we have left. We can take the derivative of this function now, so now we'll take the second derivative, which is indicated by this double prime up here. So we get for the first part, well, it's going to be 3 times 2x plus 8, which simplifies down to 6x plus 8. Now we can take our third derivative, which is the derivative of what we did previously. The derivative of 6x plus 8, well, the derivative of 6x leaves us with 6, and the derivative of 8 is 0. So now we just have 6. And finally, we can take the fourth derivative in parentheses, and we'll just get 0. We can also take the fifth derivative, but the derivative of 0 is again 0, and it will be from now on. So with polynomials, at least, once you start taking derivatives, they're going to get simpler and simpler and simpler. But this isn't always the case. What can happen is some really interesting things. So here's another question you should work on for class tomorrow and think through. If f of x equals sine of x, then which of the following statements are going to be true? And finally, there's a whole slew of extra problems to look at. So this first one and this second one you should work on for class tomorrow. They shouldn't be that bad to figure out. This third one here and the fourth one are going to be for bonuses. These will get you extra credit on the next exam, 1 point each. So the first one is to find a continuous function whose first derivative is not continuous. Next, find a continuous function whose first derivative is continuous but second derivative is not. Then find a continuous function whose n minus first derivatives are continuous, so it's continuous for a long time, but eventually it's not continuous. Does there exist a function all of whose are continuous? All the derivatives are continuous. These are really neat things. These are called smooth functions. They're really nice because when you draw their graphs, they're what you would think of as smooth. There's nothing sharp or crazy going on. So work on these problems for tomorrow. So there was the previous problem in the video, there's these ones, and as always, post a question to Blackboard and take the quiz online. Thanks.